in this lesson, we'll introduce infinite limits. Let's begin with this example. We want to find the limit of 3 over x minus 2 when x approaches 2. We cannot plug in 2 here because 2 is not in the domain of this function. Therefore, we are going to build a table and then choose x values from both sides of 2 and then observe what's going to happen on the y values, right? So let's say when x is 1.5, let's look at from the left first. When x is 1.5, and then we have 3 over 1.5 minus 2, which is 3 over negative 0.5, and then we will get negative 6. And when x is 1.9, 3 over 1.9 minus 2, which is 3 over negative 0.1, negative 30, right? And then when x is 1.99, it will be 3 over negative 0.01, and it will be negative 300. Similarly, we can do that. 3 over the negative 0.001, which is negative 3,000. And now we probably get some idea when x is approaching 2 from the left, we see the values of f is getting larger and larger, but in negative direction, right? So therefore, we can also at the same time take a look at the graph. When x is approaching 2 from the left side, and it's getting more negative. So eventually, it's going down to infinity. And what happens when x is approaching 2 from the right? We can also find the y values using these x values. So when x is 2.5, 3 over the 2.5 minus 2, which is 3 over 0.5, it's going to be 6. And when x is 2.1, 2.1 minus 2 on the bottom, which is 0.1, 3 over 0.1 is 30. Similarly, this will be, you can quickly verify, 300, and this is 3,000. And the graph-wise, we can see that when x is approaching 2 from the right, the values of y is getting larger and larger. It's going to be going up indefinitely. So in this case, we can see that this behavior is denoted as the following. When x is approaching 2 from the left, it's going downwards indefinitely. We denote it as negative infinity. And when x is approaching 2 from right, this function is increasing without bound. So we denote this as infinity. A limit in which f of x increases or decreases without bound, just like how we show here. As x approaches a certain number c, that's called the infinite limits. So these are called infinite limits. However, please do note that these symbols, they do not represent a number, and it's just a way to represent the limits does not exist, but provides a little more information. And when this limits doesn't exist, we know it's going decreasing indefinitely, and this is increasing indefinitely. All right, now let's introduce the formal definition of the infinite limit. Assume that f of x exists for all x in some open interval containing c, except possibly at c. And this statement, limit of f of x when x is approaching c is equal to infinity, means the following. For each m greater than 0, there exists a delta greater than 0, such that the function value f of x is greater than m whenever x minus c is absolute value of x minus c is less than delta and greater than 0. So what does that really mean? That means for each m, that means you give me any arbitrarily large number m, there exists delta. That means I can find a delta so that so that whenever this happens, that means the x values, as long as x value is within delta range around this c, then this f of x, the function value, is always larger than the value that you choose. Because this m can be arbitrarily chosen, it means it can be arbitrarily large. So when this happens, this implies f of x has to be approaching infinity, infinitely not large, because it's always greater than an arbitrarily chosen large number. Similarly, this statement means for each n less than 0, so this n can be arbitrarily chosen negative number, we can always find a delta, so that when x minus c is within this delta range, your function value is always less than the arbitrarily chosen negative number, because this number can be chosen arbitrarily large with a negative sign. That means this f of x is going to be approaching negative infinity. To define the infinite limit from the left, it's defined similarly. We just need to specify, okay, here this x is approaching c from the left, so it's inside the range from c minus delta to c. And the infinite limit from the right will be, the x will be restricted from the range that's to the right of c. So graphically speaking, so this means when x is approaching c from the right, the limit is going to infinity here. When x is approaching c from the right, this means the limit is approaching negative infinity. So that means those two. When x is approaching c from the left, when this happens, we denote it as f of x is the limit is equal to infinity. And when x is approaching c from the left, and when f of x is going downward, we denote it as negative infinity. Let's now define the vertical asymptote. We'll call a line x equals c, there's a typo here, x equals c, a vertical asymptote of a function f when any one of the following happens. In other words, if the limit of f at c is either equal to plus or minus infinity, or any one of the one-sided limits is equal to infinity or negative infinity, then when that happens, we are going to call x equals c as a vertical asymptote. The next theorem provides us a way to find the vertical asymptote. This theorem says f and g are continuous on open interval containing c. If f of c is not equal to 0 and g of c equals 0, that means this is not equal to 0 and this is equal to 0 at c. Then x equals c is going to be the vertical asymptote. Now let's work on some problems. Let's take a look at the first one using the graph. The graph of function is given here. Let's identify the following. The first one is the limits when x is approaching 1 from the left. Approaching 1 from the left. We can see that the function value is growing without bound. Therefore, the limit will denote it infinity. And when x is approaching 1 from the right here, when x is approaching 1 from the right, and we trace this function, and it's growing without bound also. So therefore, this is infinity as well. And because these two one-sided limits, they are approaching to the same direction, so therefore we are going to say the limits when x is approaching 1 is infinity. Again, this doesn't mean the limits exist. It's just telling us that the function value is increasing without bound. It still means doesn't exist. When x is approaching 2 from the left, so from the left, let's trace the function, and it's growing without bound, right? So therefore, this is infinity. And when x is approaching 2 from the left, this time it's decreasing without bound. So therefore, this is negative infinity. And how do we correctly, appropriately answer this, the next one, the limits when x is approaching 2? Because both limits, they are not approaching the same direction. One is infinity, the other one is negative infinity. Here we will have to say this does not exist. Well, again, this one means doesn't exist. However, we want to use infinity instead of doesn't exist because this gives us a little more information about how the function behaves. And then we use does not exist here because these two are not representing the same direction of the infinity. Let's find some vertical asymptotes for the following functions. So first of all, the previous theorem tells us we have to make sure that the vertical asymptote happens when the denominator is equal to 0, right? So here, because x squared plus 1 will never be equal to 0 for all values of x, right? Therefore, we don't have any vertical asymptote. Vertical asymptote for this particular function. Now let's take a look at the second function. And the vertical asymptote happens when the value will make the denominator 0, but not the numerator. So therefore, let's set the denominator to 0. X squared minus 4 equals 0. And this gives us two values, plus or minus 2, right? And let's make sure that these two values won't make the numerator 0. And x squared is not equal to 0 when x is equal to plus or minus 2. And because of that, we can make a conclusion. Therefore, x equals 2 and x equals negative 2 are both vertical asymptotes. Next, let's look at x over sine x. So my first step is to find the values so that the denominator is equal to 0. And sine x, this is a periodic function, and it is sine x equals 0 when x is equal to 0, pi, 2 pi, 3 pi, and so on and so forth. And of course, negative pi, negative 2 pi, and so on and so forth. So basically, it's a multiple of pi, n times pi, where n is integer. So let me use this symbol. N belongs to an integer, z means integer. However, we want to make sure that the numerator is not 0, right? And let's check. Actually, when n is 0, that means x is 0. This is 0. So in that case, that should be excluded there. So, however, when x is equal to 0, this limits x approaching 0, x over sine x, becomes 0 over 0 type, right? In this case, we cannot just do this regular substitution. And if you remember, so in the previous lesson, the limits of this guy, sine x over x, is equal to 1. So therefore, this actually is equal to 1, this limit, and it is not one of the infinity or negative infinity. So therefore, x equals 0 is not a vertical asymptote. However, for all other values of x here except x equals 0, the numerator won't be 0. Therefore, those will be the vertical asymptote. So therefore, I'm going to make a conclusion here. Therefore, x equals 0 is not a vertical asymptote, and x equals m pi when n is not equal to 0 and n is any other integer, that will be a vertical asymptote. Or vertical asymptotes. Let's look at the next example. Here, step 1, you want to find the values so that the denominator is equal to 0, right? So in this case, x squared minus 4 equal to 0, x is plus or minus 2. Plus or minus 2. However, you don't want to just say the vertical asymptotes are x equals 2 and x equals negative 2. You have to make sure the numerator is not equal to 0. And actually, however, in this case, if you look at the limits when x is approaching negative 2 of this guy, and we did this kind of problem earlier, and so when we cannot do the direct substitution, we have to first factor the denominator, right? And we can see that these two cancels, and then after we cancel, we can plug in the do the substitution. So when we plug in negative 2 for x, we have 1 over negative 4, and this guy is not equal to infinity or negative infinity. Therefore, this is not, x equals negative 2 is not going to be a vertical asymptote. So only x equals 2 is a vertical asymptote. In the next example, we're going to find the limits analytically. That means without using graph, only use critical thinking or logical thinking. Well, the first one, x approaching 3 from the right for this function. First of all, you should always try to do a substitution in your first attempt. Here it won't work because the numerator is not equal to 0, but the denominator will be equal to 0. So we have to, we cannot do the direct substitution. Now let's do a little analysis here. When x is approaching 3 from the right, usually I like to draw a little diagram. This is 3. X is approaching 3 from the right. That means x is greater than 3, right? These values should be greater than 3. But it's approaching 3. Therefore, the bottom is approaching 0. So I'm going to say the bottom approaching 0. But with the positive sign, right? Because its x values are larger than 3, so it's going to be positive. And the top 2 minus 5x is going to be approaching 2 minus 5 times 3, which is 2 minus 15, which is approaching negative 12. So this is approaching approaching negative 12. So therefore, we have negative 12 over a positive, very, very tiny number. So this actually provides us negative infinity, right? You can think of a negative number divided by a very, very tiny but positive. So the ratio will be negative infinity. Similarly, for the second one, the same function, exactly the same function, but this time x is approaching 3 from the left, meaning x is somewhere here. And because x is less than 3, so to the left side, so this number should be approaching 0 but negative sign, right? So here I'm going to say this guy approaching 0 but negative. And here this is still approaching negative 12. And because there's a negative sign, there's a top and bottom here, so the ratio should be positive. Therefore, this result is positive infinity. So there's not much calculation that you do. You just have to be very careful on the sign so that you know whether the result is infinity or negative infinity. And now if I ask you this question, limit x approaching 3 to minus 5x over x minus 3, what is that equal to? Then you can see that we just did the right limits and the left-sided limits, right? And one is approaching negative infinity, the other one is positive infinity. They are not the same, so therefore we will have to say does not exist. Now, if I just start with this question instead of this one-sided limit, hopefully you will you are aware that you have to look at both sides to make sure that whether they are the same or not before you make this conclusion. The next example, we will find the limits when x is approaching 0, x minus 5 over x squared. The numerator will be approaching negative 5, 0 minus 5 is negative 5. The denominator is approaching 0, and because of the square, regardless, the sign of x, either negative approaching left or right, because of the square, it guarantees positive, right? So therefore approaching 0, but positive. So with negative 5 over a 0, a number approaching 0 with positive sign, this will become negative infinity. We don't really, we already kind of discussed the left and right limits, and because of the square, that guarantees to be positive. And last one, this time when x is approaching 2, we want to look at 3 over x minus 2. So when you plug in 2, this will be 0. You cannot just based on that you say does not exist. We want to know more specific. Is that positive infinity, negative infinity, or it really doesn't exist? That means left and right limits do not agree. So we'll have to look at the left and right limits. Let's look at the left limits first. So when x is approaching 2 from the left, this means this. This means x is less than 2, right? Going from this direction. And in this case, this is, well, the top is 3. Here, this is approaching 0. So let me use this arrow sign to represent approaching 0, but negative, right? But negative. So I would not write this in my formal writing. This is just how I will explain it. So a non-positive number divided by a negative number, the result will be negative, and will be negative, and then infinity. when x is approaching 2 from the right. So in this case, these two x is greater than 2. Therefore, x minus 2 will be positive and approaching 0. 3 over a positive number but approaching 0, this is going to be infinity. Because they are not the same here, I would say this time does not exist. Will be the most appropriate answer. Lastly, let's talk about the properties of infinite limits. It's pretty intuitive here. Let's C and L be real numbers, and f and g be functions such that the limits of f of x when x is approaching c is infinity, and but the limit for g will be L. And the sum and difference will be the limits of this sum or difference of these two functions will be infinity. This is pretty intuitive because this f is approaching infinity and this is approaching L. Well, infinity definitely dominates this result, right? So the result will be the limits of this f of x, which is infinity. The products will be if L is positive, like the limits of this guy is positive and this is infinity, then the result will be positive infinity. If this L is negative, in other words, the limits of g will be negative and this is infinity, the result will be negative infinity. The quotient, because g is a limit of g is a number L and the limits of f is infinity, so a number over infinity will be 0. And similar properties hold for one-sided limits and for functions for which the limits of f as x approaches c is negative infinity. We just do the appropriate adjustments. Let's take a look at the following examples. So the first one, limits when x is approaching 1 of the following function, 7 minus 1 over x minus 1 squared. And because the limits of the first function is 7, right? 7. And the limits of the second function, this time when x is approaching 1, due to the square of the x minus 1, it guarantees this positive. So it's a positive number but approaching 0, so therefore this is infinity. So 7 minus infinity in this case will be negative infinity. Now when x, for the second one, x is approaching pi, and the numerator is approaching pi, so this is approaching pi. And the bottom one approaching 0, right? Sin pi is 0. However, we have to be careful now. And if you remember the sine, the graph of sine, this is the pi. And we can see when x is approaching pi from the left, sine is positive but approaching 0. But when x is approaching pi from the right, sine of x will be approaching 0 but negative sign. So for that reason, this actually doesn't exist, right? So I'm going to write this down. The limit x approaching pi from the left, x over sine x, is actually positive infinity because from the left, sine is positive, so positive infinity. And when x is approaching pi from the right, this actually will be negative infinity. Because of that reason, I'll have to say does not exist because they're not the same. Lastly, let's look at this example. X squared times secant pi x. Well, if you remember, secant pi x is actually 1 over cosine, right? 1 over cosine. And when x is approaching 1/2 from the right, So therefore, let's take a look at cosine, okay? Cosine function. So when x is approaching 1/2 from the right, we want to look at cosine pi, half over pi, okay? But from the right, Now, cosine, so this is pi over 2. When cosine pi over 2 from the right, it's approaching 0 but less than 0. It's negative. So in other words, with that, we know this is approaching 0 but negative, right? But negative sign. So because of that reason, now we can say this is equal to, this is a positive number, 1/2 square is positive, over a 0 but negative sign. This is going to be negative infinity. Alright, that's it. This is all we want to talk about the infinite limits in this lesson.